Every second of every day, billions of people depend on electricity without giving much thought to where it comes from. Lights switch on instantly, hospitals power life-saving equipment, factories operate around the clock, trains move across entire countries, and data centers keep the internet running. While many power plants generate electricity by burning coal, natural gas, or oil, some of the world's most powerful energy facilities operate in a completely different way. Instead of burning fuel, they unlock the enormous amount of energy stored inside tiny atoms. This process takes place inside a nuclear reactor, one of the most advanced engineering systems ever created. Using controlled nuclear reactions, a single reactor can produce massive amounts of electricity for millions of homes, while using only a relatively small amount of fuel. Behind this remarkable technology is a combination of physics, precision engineering, multiple safety systems, and decades of scientific innovation that work together every hour of every day. The story of nuclear energy begins with the atom, one of the smallest building blocks of matter. Everything around us, including water, air, rocks, and even our own bodies, is made of atoms. At the center of every atom is a tiny nucleus that contains protons and neutrons. In certain elements, such as uranium, the nucleus is naturally unstable. Scientists discovered that if a uranium atom absorbs an extra neutron, its nucleus can split into two smaller atoms. This process is known as nuclear fission. When the atom splits, it releases an enormous amount of heat along with additional neutrons that can trigger the splitting of other uranium atoms. If carefully controlled, this chain reaction becomes a reliable source of energy capable of producing electricity continuously for many months. The fuel used in most commercial nuclear reactors is uranium, a naturally occurring metal found in rocks around the world. Before it can be used inside a reactor, uranium must go through several processing stages. It is mined from underground deposits, purified, converted into uranium dioxide powder, and pressed into small ceramic pellets. Although each pellet is only about the size of a fingertip, it contains an incredible amount of stored energy. Thousands of these pellets are stacked inside long metal tubes made from special alloys that can withstand high temperatures and intense radiation. These tubes are called fuel rods, and hundreds of fuel rods are grouped together to form fuel assemblies that are placed inside the reactor core. At the heart of every nuclear power plant is the reactor vessel, an enormous steel container designed to safely contain the nuclear reaction. Inside this vessel, dozens or even hundreds of fuel assemblies are carefully arranged to create the reactor core. As uranium atoms undergo controlled fission, they release a tremendous amount of heat. Unlike an explosion, the reaction inside a power reactor is carefully regulated so that only a controlled number of atoms split every second. This steady release of heat allows the reactor to operate safely while producing a constant supply of energy. Keeping the nuclear reaction under control is one of the reactor's most important functions. This is achieved using control rods made from materials such as boron or cadmium, which are highly effective at absorbing neutrons. By moving these rods deeper into or farther out of the reactor core, operators can precisely control the number of neutrons available to continue the chain reaction. Inserting the rods further slows the reaction, while withdrawing them increases power output. If an emergency occurs, the control rods can be inserted completely within seconds, bringing the chain reaction to a rapid stop. This automatic shutdown process is one of the primary safety features found in every modern reactor. Another essential part of the system is the coolant. As the uranium fuel releases heat, the temperature inside the reactor core rises rapidly. To prevent overheating, a continuous flow of coolant removes this heat from the fuel assemblies. In most nuclear power plants, ordinary water serves as both the coolant and the moderator. The moderator slows down fast-moving neutrons, making them more likely to trigger additional fission reactions. At the same time, the water absorbs heat from the fuel rods and carries it away from the reactor core. Powerful pumps keep the coolant circulating continuously, ensuring that temperatures remain stable throughout operation. The heat collected by the coolant is then transferred to another part of the power plant, where electricity generation actually begins. In pressurized water reactors, the hot coolant flows through large steam generators. These massive heat exchangers transfer thermal energy to a separate supply of water without allowing the two systems to mix. As the secondary water absorbs heat, it turns into high-pressure steam. This steam becomes the driving force that powers the rest of the plant. The high-pressure steam travels through large pipes until it reaches the steam turbine. A turbine is a massive rotating machine fitted with hundreds of carefully engineered blades. As the steam rushes across these blades, it causes the turbine shaft to spin at extremely high speeds. Some turbines rotate at approximately 3,000 revolutions per minute, converting the energy contained in the steam into powerful mechanical motion. Although the nuclear reactor produces heat, it is actually the spinning turbine that provides the mechanical energy needed to generate electricity. Connected directly to the turbine is an electrical generator. Inside the generator, large electromagnets rotate within coils of copper wire. According to the principles of electromagnetic induction, this rotating magnetic field produces an electric current. This is the same basic principle used in hydroelectric dams, wind turbines, and fossil fuel power stations. The only major difference is the source of heat used to produce the steam. In a nuclear power plant, that heat comes from controlled nuclear fission instead of burning fossil fuels. After passing through the turbine, the steam has lost much of its energy. Instead of being released into the atmosphere, it enters a condenser where it is cooled back into liquid water. Cooling water from nearby rivers, lakes, or the ocean absorbs the remaining heat without mixing with the steam itself. Once condensed, the water is pumped back to the steam generators where the entire cycle begins again. This closed-loop system allows the plant to recycle enormous quantities of water while operating continuously for months without interruption. The electricity produced by the generator cannot be sent directly to homes because its voltage is relatively low. Instead, it first passes through massive transformers that increase the voltage to hundreds of thousands of volts. High-voltage transmission allows electricity to travel long distances while minimizing energy losses. From the power plant, electricity flows through transmission lines to substations where the voltage is gradually reduced before being distributed safely to homes, schools, hospitals, businesses, and factories. Because nuclear reactors involve radioactive materials, safety is built into every stage of their design. The fuel pellets are enclosed inside sealed fuel rods, which are placed within the thick steel reactor vessel. Surrounding the vessel is a reinforced concrete containment building designed to withstand earthquakes, severe storms, and even certain external impacts. Multiple independent cooling systems, backup diesel generators, emergency batteries, and automated shutdown systems provide additional layers of protection. Modern reactors are designed using the principle of defense in depth, meaning several independent safety barriers work together so that even if one system fails, others continue protecting the reactor. Highly trained engineers and reactor operators monitor every aspect of the plant 24 hours a day. Thousands of electronic sensors continuously measure temperature, pressure, neutron activity, coolant flow, radiation levels, and equipment performance. Advanced computer systems analyze this information in real time, allowing operators to respond immediately if any abnormal condition develops. Regular inspections, preventive maintenance, and strict international safety standards help ensure that every reactor operates safely throughout its service life. One question many people ask is, what happens to the spent nuclear fuel after it has been used? Although fuel assemblies gradually become less efficient over time, they still contain valuable materials along with radioactive elements. After removal from the reactor, the used fuel is placed inside deep cooling pools where water removes residual heat while also providing radiation shielding. Later, the fuel may be transferred into specially designed dry storage containers built to safely contain radioactive materials for many decades. In some countries, portions of the spent fuel are also recycled to recover useful nuclear materials for future use. Despite common misconceptions, nuclear power plants do not release smoke from their cooling towers. The large white clouds often seen rising above these towers are simply water vapor, similar to the steam produced by boiling water. Because nuclear reactors do not burn fossil fuels during electricity generation, they produce extremely low carbon dioxide emissions while operating. For this reason, many countries consider nuclear energy an important part of reducing greenhouse gas emissions while maintaining reliable electricity supplies. Technology continues to improve the next generation of nuclear reactors. Engineers are developing small modular reactors, often called SMRs, that are easier to build, require less land, and include advanced passive safety systems capable of operating even without external power. Researchers are also exploring advanced reactor designs that improve fuel efficiency, reduce radioactive waste, and increase overall safety. These innovations may play an increasingly important role as global electricity demand continues to grow. Although the science behind nuclear energy is highly complex, the basic principle is surprisingly straightforward. A controlled chain reaction releases heat. The heat produces steam, the steam spins a turbine, and the turbine drives a generator that produces electricity. Through advanced engineering, multiple safety systems, and decades of scientific research, nuclear reactors have become one of the world's most reliable sources of large-scale electricity. Every time a light turns on, a hospital performs life-saving surgery, or an entire city continues operating without interruption, there is a good chance that the energy making it all possible began inside a carefully controlled nuclear reactor, where the power locked within atoms is transformed into electricity that supports modern life every single day.